Related rates. To discuss related rates, I'm going to pose three scenarios, and I would like you to ask yourself, what do the following scenarios have in common? Here is the first scenario. Someone is inflating a spherical balloon. You know the rate the volume is increasing. When the radius is 4 inches, you are asked to find the rate at which the radius of the balloon is increasing. Scenario 2. A ladder leaning up against the wall starts to slide down the wall at a known rate. When the base of the ladder is 4 feet from the wall, you are asked to find the rate at which the base of the ladder is moving away from the wall. Scenario number 3. Suppose price would not affect demand, and the revenue is constant. When the price is $10 and the demand is set for 20 items, you knew how fast the demand was dropping and were asked to find how the price was changing. What do the following scenarios have in common? First of all, each of these following scenarios deals with rates that are related to one another, appropriately termed related rates. Related rates refer to a problem where one compares the rate one quantity is changing to the rate another quantity is changing. What do the following scenarios have in common? More specifically, with each of the three scenarios, we are asked to find a rate. In the first scenario, we are asked to find the rate at which the radius of the balloon is increasing. In the second scenario, we are asked to find the rate at which the base of the ladder moving away from the wall. And in the third scenario, we are asked to find how the price was changing. What else do these three scenarios have in common? They freeze a moment in time, somehow. Let's see how. In the first case, they stop the inflation of the balloon when the radius is 4 inches, freezing a moment in time. In the second case, we have a ladder sliding down a wall. We ask the question at a moment frozen in time, when the base of the ladder is 4 feet from the wall. And in the third scenario, we are asked to take a look at the relationship of revenue, price, and demand at a particular moment when the price is $10 and the demand is for 20 items. What else do they have in common, these three scenarios? A known rate for one of the quantities is provided. In other words, we know the rate the volume is increasing. In the second case, we are going to know the known rate that the ladder starts to slide down the wall. And in the third case, we know how fast the demand is dropping. So let's look at the first scenario. Specifically, here is the scenario. Someone is inflating a spherical balloon at a rate of 2 inches cubed per second. So inches cubed is a volume per second per time. When the radius is 4 inches, find the rate at which the radius of the balloon is increasing. Let's use our rubric. Find a rate. Well, what are we asked to find specifically? We're asked to find the change the radius is experiencing as this volume increase, a change of radius per time. A moment frozen in time. Well, for the moment frozen in time, R equals 4. And we are given a known quantity, rate of change. That is, the balloon is inflating at 2 inches cubed per second. That's a change of volume with respect to time. Now we have a change of volume when radius is frozen at 4 inches. So we want a relationship between those two quantities, volume and radius. In other words, do we have a formula that relates them? We do. The volume of a sphere is 4/3 pi r cubed. So we begin the process. When you solve related rates once you have designated what is given and what you're asked for, you write down a formula, and a rate of change is a change of a quantity per time. So we differentiate both sides of the equation with respect to time. dv dt is equal to 4/3 pi, and then we take the derivative of the radius cubed. So we have dv dt is equal to 4/3 pi times the derivative of r cubed, 3r squared. But again, as time increases, the volume is growing and the radius is growing. In fact, the point of the problem is to find how the radius is changing at a particular time. The point I'm trying to make is that the radius depends on time. We have a chain rule, times dr dt. Now we substitute in the given, the change of volume per time, 2, the radius, 4, and the only variable we have, I'll underline, dr dt. So we solve for it. Isolating dr dt, we have 2 equals 64 pi, and dividing through by 64 pi, we have 2 over 64 pi, and that reduces to 1 over 32 pi inches per second. In other words, when the volume is changing at 2 inches cubed per second, and we freeze the moment when the radius is 4 inches, at that moment, the radius is changing by 1/100th of an inch per second, approximately. Let us look at the second scenario. An 18-foot ladder leaning against a wall starts to slide down, and will slide down the wall at a rate of 5 feet per second. When the base of the ladder is 4 feet from the wall, we are asked to find the rate at which the base of the ladder is moving away from the wall. This may require a picture on our part. So we sketch a wall. Does that look like a wall to you? We sketch the floor and prop it up against a ladder. We have a height, and we have a base, B. B stands for the distance the base of the ladder is from the wall. The ladder itself is how long? 18 feet. So we use our rubric, and we say to ourselves, what are we looking for? We're going to find a rate. So we're asked to find the rate the base of the ladder is moving away from the wall. So we're looking at a change of base per time. dB dt. We need a moment frozen in time. This ladder is sliding down the wall. We're going to stop this physical motion when? Well, when the base of the ladder is 4 feet from the wall. So when that occurs, when the base is 4, we are asking the question, how fast is the base moving away from the wall? To have a related rate problem, we need a rate. We're given a rate. What rate are we given? What's our known rate for one quantity? Well, this ladder is sliding down the wall. So we see that it's sliding down the wall at 5 feet per second. And if you can imagine a Cartesian coordinate system, and going up is a positive y, going down negative y. So we're looking for a change of height per time, and the rate is negative 5 feet per second. Now, what's the relationship between the quantities? I refer you back to this figure that we have sketched. Do you see a Pythagorean theorem? Height squared plus base squared is 18 squared. Now, what are we given? Well, if I write down this equation, I would like to differentiate with respect to time. Derivative of b squared is 2b, but the base is going to change its position with respect to time. It's going to be changing with respect to time, as well as the height. Derivative of h squared is 2h. Again, times chain rule, dh dt. The height is changing with respect to time. 18 squared is a constant. Differentiating a constant gives you 0. To substitute in values, it seems we have a value for the base. That's highlighted in red. That's 4. We have a value for the change of height per time. That is -5. But notice we're missing two variables, dB dt, if we want to think of it as what we're solving for, as well as what? As well as the height. So we go back to our Pythagorean identity and say to ourselves, we're freezing this moment when the base is 4. So we substitute 4 in for b, and now we can find h. At the moment we froze in time, when the base is 4, there is a relative height. We'll find it. We'll solve for h squared. 18 squared minus 4 squared is 308. We'll take the square root of both sides, and after reducing, we get 2 times the square root of 77. Now we have all the variables in our equation, except for the rate we need to find, dB dt. So we substitute in, replacing b with 4, replacing h with 2 times the square root of 77, replacing dh dt with -5. Solving for the change of base with respect to time, we first begin by simplifying. 4 times -5 is -20 times the square root of 77. And then we isolate dB dt to get 20 times square root of 77 over 8, or 5 times the square root of 77 over 2 feet per second. So, when our 18-foot ladder starts to slide down the wall at 5 feet per second, the base is moving away from the wall at nearly 22 feet per second. Let us look at the third scenario. The third scenario says suppose price would not affect demand and the revenue is constant. When the price is set at $10 and we're demanding 20 items per day, the demand is dropping 2 items per day each day. 2 items per day, if you will. A change of the demand, which is 20 items per day, each day. We're looking for the rate at which the price was changing. Returning to our rubric, we want to find a rate. Well, what rate are we charged with finding? Well, we would like to find the rate the price is changing. So we are looking for dP dt. We are freezing a moment in time. How do we do that? Price and demand will vary, but we're freezing the moment in time when the price is 10 and the demand is 20 items per day. So in our language, P is 10 and demand, Q, is 20. We must be given a known rate to relate it to what we're looking for, an unknown rate. What rate are we given? Well, the demand itself is dropping 2 items per day each day. -2 items per day, if you will. Now, the relationship we have between the quantities that we're given, which is revenue, price, and demand, revenue is equal to price times demand. This is our function we're going to differentiate. This is a product. This differentiation is the product rule. The change of R with respect to T is the change of the price with respect to T times demand, plus the price times the change of the demand with respect to time. Substituting in our given, since the revenue is constant, its derivative is 0. Substituting in a demand of 20 items per day, a price of $10, and a change of demand of -2 items per day, the only variable we have in our equation is what we're looking for, change of price per time. So we simply solve for it. We take 10 times -2, get -20, isolate the derivative, dp dt, and we find that we would need to raise the price $1 per day. Thank you.